Hi, this video we're gonna talking about Shear's stress strain curve, and I encourage you to look at the YouTube video by structural engineer, and that was very awesome explanation on how to get the stress strain curve. Now here I'll just do a quick recap on what's the main points here. So for stress strain curve, we'll have stress as your y and strain as your x-axis. So this is certainly normal, right? Normal stress and normal strain. And each material gonna have its own stress strain curve, and typically you will have this linear line that's elastic erosion, and then you have yielding, you have strain hardening, and then you eventually get into fracture right here. So there are three things that are very important on this graph. The first one is in that elastic erosion. What's the slope here? And E. And here, what's our E? That's a slope in the elastic region. We call this elastic modulus, or modulus of elasticity, or some people call Young's modulus. Okay, so how do we define this? Since it's slope, it's going to be rise over run, and rise will be your stress, and run will be your epsilon. And this is the highest limit when it's still proportional, follow this elastic erosion. And this one, often we use sigma yield strength. So Y means yield. Yield means this, if you're going to go a little bit even more here, what's happening is no longer go back to its original shape. It's going to have permanent deformation. So it's beyond elastic region anymore. So we here going to add our subscript yield strength and our yield strain. So stress over strain. That's going to be our epsilon yield. Okay. Then another important concept is this highest point on your stress strain curve, and we call this ultimate, right? That is the highest stress happening in the material. That's ultimate stress. Okay, that's the highest value. The third one is going to be this fracture stress. Okay, so those are the three important elements here. So here I want you to thinking about what we're talking about design previously. We have this concept called allowable stress. Remember, allowable stress is equal to the failure stress divided by safety factor, right? And what is failure stress? At the time we talk about failure stress is proprietary to that material. You know, each material gonna have its own failure stress. But what's going to be the failure stress illustrated in the stress strain curve? You could have possibility using. You could use yield strength. Why? Because at that point, you will start to yield. You will no longer have original shape, which is pretty scary, right? You're going to have a structure that's no longer going back to its original shape, have permanent damage now. Or you can use this ultimate, the highest point in your stress strain curve, or you can have this fracture point. So depending on if you're a risk taker or not, and if you're a risk taker, you can say, okay, I'm going to use the ultimate strength. And if you're conservative, you said, I'm going to use yield strength, right? And so here we often use the yield strength for our failure stress. So this is help us to connect what we learned before for the design with the stress strain curve. Okay, another concept I want to go over is instead of normal, we're going to have a shear stress strain curve. For that one, we will have the similar pattern. However, instead of the epsilon for normal strain, we're going to have a shear strain, which is what? Which is our gamma. And here, instead of epsilon, we're going to have our tau for our shear stress. And they will have a similar pattern. Okay, their value not going to be the same. For example, the tau yield strengths, they are not going to be equal to epsilon yield strength. Okay, but they have the similar trend. Now, instead of the slope here, instead of E for Young's modulus, we're going to have a new parameter we're going to call G. So G is going to be called modulus of rigidity, or you can call shear modulus. And equation for shear modulus G is gonna be equal to, since it's a slope, it's gonna be tau yield over not epsilon, gonna be our gamma yield strength. So that's gonna be our shear modulus to look at together compared to E, Young's modulus or elastic modulus. Okay. So here I want you to make sure you start to look at the book, the table of your inside of your back cover of Hebler book. That shows all those information. You can find your yield, you can find shear, you can find Young's modulus or modulus of elasticity, or you can find the modulus of rigidity or shear modulus. All those information is in there. So start to look at that, to using it to solve your problems. Okay, all right, that's all for a quick review on stress strain curve. But I think I'm missing something. I'm actually gonna write down this really quick. I'm gonna make a quick table to look at normal and shear. So for normal, internal force, and we also talk about stress. And now we also talk about strain, and we have now correlate stress and the strain here in this curve. So normal force is N. Stress is gonna be sigma equal to N over A. And strain is gonna be epsilon. It's gonna be changing length over original length. And shear is going to be V. And our shear stress tau is going to be our V over the area where the shear force acting on. And our strain, our gamma has a couple of expressions. You can have pi over 2 minus theta prime, or equal to theta equal to opposite over adjacent. Remember, all those have to be in radians for those angles. Okay, now we're also talking about to relate stress and strain, especially in elastic region. We have Hooke's law. We have elastic modulus is going to be equal to sigma over epsilon. Same thing applied to the shear. then we have G equal to tau over gamma, right? So that's all we have to quick recap of the stress strain curve. That's all. All right. See you next time. Bye now.